Okay, so I'm the director of the Large Binocular Telescope Observatory, and I'm pleased to give you an update on the status of the observatory and some exciting prospects going forward. So let me start with some background, which is that, okay, something got a little strange here in the PowerPoint, but the summary point is clear, which is that the observatory is an international collaboration with 50% participation from Europe and 50% from various universities in the US. And the particular takeaway here is that we circled Germany, but that should have been circling Arizona, okay, because Arizona is 26% of the participation of this observatory. And it is a private observatory, which means you have to be somehow connected with the ownership of the observatory to get access. And as part of the U of A community, you have that. Okay, so where is LBT Observatory? It is on the summit of Mount Graham, which is northeast of Tucson. It's at an elevation of 3,200 meters, which makes that one of the highest research observatory sites in North America, which is particularly significant if you want to do mid-infrared observations that are sensitive to water vapor, because you're above a lot of it at that altitude. The defining attribute of the observatory, as you might guess from the name, is the use of two very large mirrors, each 8.4 meters in diameter. They're cast at the University of Arizona, the Stewart Observatory Mirror Lab, and that matches, that's the largest monolithic mirrors that have been made, matching the diameter of the mirrors that have been cast for the Giant Magellan Telescope. If you combine the light from both of those individual mirrors, that gives you the light collecting power of a single 11.8 meter diameter mirror. So the power of a telescope is measured by its light collecting power, but also by its resolving power. And here, if you combine the light coherently from the two sides of the telescope, the diffraction limited resolution is proportional to wavelength divided by diameter, and the relevant diameter here is the edge-to-edge spaceline, which is close to 23 meters. So by both of these measures, this is one of the most powerful telescopes in the world today for optical and infrared measurements. So on the telescope, there is now a very mature and quite sophisticated complement of instruments. They're categorized in several categories. That includes the facility instruments, which are maintained by the observatory, a comprehensive suite of instruments for optical spectroscopy, infrared imaging and spectroscopy. We have prime focus imaging cameras with a relatively large field, very powerful high resolution spectrograph, and also a mid-infrared camera. We have what are referred to as strategic instruments. Those are supported by one of the consortium members to a significant degree, and the one that's of particular interest here is the LBT interferometer, and that is the instrument that actually leverages the 23-meter baseline, achieving the full resolving power of the telescope. We also have PI instruments, principal investigators along with their teams, which support the instruments listed here, an infrared camera, as well as two relatively new instruments for high angular resolution, high contrast imaging, which I'll talk about in just a little bit, the SHARC instruments. And also coming very soon, the eye locator high resolution spectrograph, which is optimized for extremely high precision radial velocity measurements in the near infrared bandpass. So in addition to the instruments and the telescope itself, a very significant aspect of the LBT is its use and implementation of adaptive optics. And here the goal is to get around the problems caused by turbulence in the Earth's atmosphere, resulting in what astronomers call seeing. So this is the distortion that causes your nice point source shown on the left to be blurred out to a blob on the right as an incoming wavefront undergoes distortion as it passes through the Earth's atmosphere. And the solution that's been developed over the last 2 decades plus is to implement in your light chain a deformable mirror with a wavefront sensor monitoring the impact of the atmosphere. The wavefront sensor drives the deformable mirror to reverse and take out the distortion of the incoming wavefront due to that atmospheric turbulence. So at the LBT, this has been implemented very successfully in secondary mirrors, each about 1 meter in diameter and 1.6 millimeters thick for the glass surface, actuated by 672 actuators to take out this atmospheric distortion. And it's also on the second reflection in the system. Many implementations of AO, the correction occurs much further downstream. Okay, so let me show some results that are coming out of this complement of telescope instruments and AO. So here's some results from the LBT interferometer for MWC 758, which is a young A star with a circumstellar disk. It was known that the circumstellar disk has spiral arms. Spiral arms typically require some dynamical driver, and there was no dynamical driver in the form of a planet or a brown dwarf nearby that would explain that. With new mid-infrared observations with LBT, we now have a candidate identified as C. And the reason it was discovered is going to longer wavelengths. We picked this up as a very red source. It's either a very cool planet or highly obscured, and now give us an explanation for driving that spiral structure. So we now have a potential explanation for other cases for a spiral structure without an obvious companion. We have to look further in the red. And also, if we're going to do the full survey and inventory of extrasolar planets, you're going to need observations like this in order to find similar sources. Here's another result from our Pepsi spectrograph for also for extrasolar planets, in this case doing transit spectroscopy. This is for Kelt 20b, an ultra-hot Jupiter, and the measurements here are shown in black. And after removal of the telluric absorption, the atmospheric absorption, you see emission lines from this source. That's telling you there is a temperature inversion in the atmosphere of this extrasolar planet. And in order to account for that, there has to be some kind of opacity. And so it's an interesting question. What is the source of opacity? And from the new measurements, there's a very strong indication that iron 1 is the source of opacity in this system. So the Pepsi spectrograph is proving very powerful for these transit spectra studies of planetary atmospheres. Okay, I want to talk very briefly about these second generation instruments we call SHARCs rather than giving the whole long name there. There's two channels, near infrared on one side and visible on the other. They're installed in the last year and a half, and they're optimized really for extrasolar planet studies with high contrast, high angular resolution imaging, and in the near infrared channel spectroscopy. So I want to show just the power of this with the demonstration of an observation that was acquired with SHARC-Viz, looking at the Galilean moon of Jupiter Io, which everyone here knows is very remarkable and interesting for the high level of volcanic activity seen on its surface. So the SHARC-Viz image. So here is a comparison of Io, image from ground and from space in visible light and several band passes, but the comparison may not be what you think, because the space-based observation is on the left from the Hubble Space Telescope, and the ground-based SHARC-Viz observation is on the right. The science here, of course, is the ability to actually see variations in evolution of the structure of this due to volcanic activity. And you can see the very large, the famous volcanic region Pele with a sulfur ring around it. In the newer observations from SHARC-Viz at around 2 o'clock, you see that it seems to be attenuated. That is now understood to be due to a more recent layer of ejecta from an adjacent active region that has modified that region. So you can map this out from the ground with this instrument. Okay, so I hope you're convinced that if you're not using the Large Molecular Telescope, you should be. And how do you get access to this? It is scheduled on a semester basis. Time is allocated based on a proposal review to the University of Arizona telescope allocation process. Our observatory staff can help you with experimental design if there's something you want to do. The University of Arizona time is carried out in a queue mode, which means that our staff execute the observations and you get those at the end of that. So we're happy to consult. The one final note I would make is that we've had some of our investigators have been very successful in leveraging this resource to secure very significant NASA funding for projects they want to do, and that's something we're happy to talk to you about. Okay, that's all. I'm happy to answer any questions.